work focus on optimize these key kernels. Let's look more closely at these two kernels. On the left side, the IPS iteratively keeps the point that is away from all various chosen points. During each iteration, it first computes distance between the simple points and unsimple points, and find the favorite unsimple points to the simple point side. Traditional IPS work in 3D spaces. However, modern version also use feature space IPS operation in the high-dimension feature space. On the right side, the KN search is on to find close points for each array point, similar to IPS. Modern application have extended this approach to high-dimension feature space. As a result, current cloud application often combine geometric and feature space IPS and KN to reach their scale. Recently, many domain-specific accelerators have been designed for cloud acceleration. They usually include a specialized unit for IPS and KN and a syscopy for gene communication. However, these architectures are kernel independent, and that causes a problem. Different kernels run at very different speed, known to lead to a low hardware utilization. For example, in the one-night class, the hardware utilization dropped to 18%. In EDCN, the syscopy rate remained idle, with hardware utilization falling to 1.7%. To solve this, we need a unified hardware that can efficiently run both metric application and on-cloud Azure kernel. However, the different kernel prefer different execution model. The best strategy for IPS and KN vary greatly between low-dimension space and high-dimension feature space. So, one fixed computation pattern cannot be low. Design an accelerator with both memory execution model ensures significant challenges in both data path design and control logic design. As the number of computing operations increase, the proportion of common operation will become smaller and smaller. Your unique operation will cause the accelerator to take a high area overhead, which is unacceptable. So, instead of building another standalone accelerator, we turn our attention to modern CPU. Recently, the CPU have included matrix operation extension and syscopy, such as Intel's AMX and ARM's SIE extension. They are tightly coupled with the CPU pipeline and deliver high throughput. So our idea is to offload the heavy compute part of the cloud workload to such matrix extension. We'll keep control-intensive part on the CPU traditional pipeline. This will give a better balance between the performance and cost. However, this is not straightforward. Cloud kernel mostly have 1D parallelism, which represents one query point with every reference point. Well, syscopy is designed for 2D parallelism. This mismatch will limit hardware efficiency. To overcome this, we transform the algorithm from single point to multi-point pattern, which is ST2MT, to multi-point pattern, which we call MT2MT. So, in this work, we propose one ASA, a real instruction set architecture extension for efficient on-clock analytics. On the hardware side, we design a versatile syscopy that supports both metric operation and on-clock kernel. On the software side, we reshape algorithm into 2D parallelism form to fully explore the hardware. Firstly, we analyze IPS and KN kernels and computation involve complex branching statements, which are not friendly for algorithm processing units. Based on this insight, we designed new structure for computation-intensive operation, and left the other part to traditional CPU pipeline. We designed one structure for Euclidean distance computation, 3 for different sorting models, and 1 for data units. All these new instructions are integrated into LLVM with intrinsic or C code, enabling developers to directly utilize them in high-level code. For efficient execution, propose instructions with minimal hardware overhead. We designed a network 8x8 syslog view that will use existing CPU components. Each processing element has small substructure and compactor units until the net unit. The array also supports the 3 sorting mode using a 2-stage sorting pattern, which takes about 1.5 n cycles for n elements. On the left side is an example. We further optimize the algorithm to make the new assay. For IPS, we identify and deferring unnecessary distant updates. Our report generates update sample points for iteration without affecting sample accuracy. The key idea is to find the forest and second forest points in each bucket. The detail of this algorithm can be found in our paper. This increased computation intensity and reduced memory access. For GAN, we designed a lazy search method using cache queue. In simple terms, we break the search processing into small stages. Each stage focuses on one part of KB tree instead of processing the whole query at once. This makes every query run in parallel and keeps the hardware busy. As a result, we can build efficient MT2 and T patterns and fully use our IC extension. Finally, we evaluate what IC with digital simulation and neural implementation. The key parameters are shown in the table. The power is analyzed with MACPAC and example patterns, and the area is evaluated with SEC and SEC2 at the 28nm process. We have 6 applications for smart data sets and for end-to-end evaluation. The performance evaluation shows that quantum Asia achieved a speed up of 5.4 speed up compared to baseline and achieved a 4.9 times improvements in power efficiency. The area and power consumption evaluated revealed that the proposed technology occupies only 0.547 square millimeters and with 314.8 liter water power consumption, only within 0.9 area overhead for a whole CPU. We also take a closer look at MICRO25 performance pattern. The new instruction set reduced the total number of committed instructions by about 89%, and it also cut L1 cache access significantly. To understand how the behavior at runtime, we analyze the instruction breakdown of IPS and hidden. As shown on the right side, the point assay instruction make up about 20% of total instruction in IPS and 33% in hidden. This shows that this intrinsic instruction play a key role in the most computation-intensive stage. To better analyze the trade-off between general purpose and specialized drive, we compare coordination with quantizing, which is the domestic accelerator. In fact, coordination is about 17% slower because the gene operation is less efficiency for the quantification. However, on the last cell emphasized by quantize, quantize are actually perform better. This is because quantize use only brute force LTS and hidden, while quantize flexible design allow more efficient algorithm level optimization. To summarize, we propose quantize an assay extension for automatic use through architecture and algorithm design. It introduces new distance and shortening instruction, like versatile systematic and reconstructive algorithm into efficient P2P planning. Together, this design brings high performance, low overhead, and great flexibility for functional workflow. Thank you for your attention. Next question.
Any questions? Please come to the microphone.
Before you show the performance of South Asia, okay, so I found your work quite ISR is lower than the SOTA from ACC. Your error is lower. So do you have any objections to improve your performance? And make your architecture faster or smaller, also than the system.
Thank you for the question. The network is slightly slower than the quantize. This is because the gene operation is less efficient for than the quantize. In the quantize, it can run very efficiency and the system operate always easy for the matrix application. However, in the quantification, the CPU issues the instruction about 3 cycles per instruction, so it will run slower than we can use the kernel fusion and matrix through RAM to speed up this process.
Any other questions from the audience? So I have a question. Sorry for my detail. The previous papers had this target of 30 frames per second as their full latency. Is there an equivalent target in this area? Is there a target in frames per second for the quantified system? And how close is your quantize to that?
In the application, it must